Yes, Memuna, is it audible to you?
Yes, ma'am.
Okay. So, in the last class, we had stopped at this point where we had completed the resistance part. Now, a new topic, terminal potential difference. So, terminal potential difference, internal resistance, and EMF. These are three topics which we have to deal with right now. These are short topics. We'll be able to finish it in one class itself. First, we'll start with internal resistance. Now, see, I'll draw the structure of a battery. See, suppose this is inside of a battery. What is filled? There are, when you see the structures, two electrodes are present. These are electrodes. And these are dipped in electrolytic solution. So this is what? This is a battery, or you can say a cell. And these two are the electrodes. And this is the electrolytic solution. Now, what happens in this? Whenever, now see, you know that these, what happens to these two? These are further connected to the circuit. These are further connected to the circuit. So what happens? When you have this battery, when you have this setup, one is positively charged, another one is negatively charged. So the ions are released within the electrolytic solution. Electrons move within this electrolytic solution and reaches the negative part and then goes on to the circuit. This occurs within the simple battery which we see. We don't see the inside portion, we just see this part. And in the circuit also, we simply draw it like this. So actually this happens. Now, whatever resistance and opposition is felt when these electrons are moving, when they are moving, whatever resistance, whatever opposition is felt, that is called as internal resistance. So it is the resistance offered by electrodes and electrolytic solution of the cell. This is internal resistance. Write it, Memuna. Then I'll start with EMF. Then we'll see how all these three are related. Okay, Memuna. Let's come to EMF. Now see, you will see two terms. Electromotive force, EMF, and second term, terminal potential difference. Now, when you see both of these terms, terminal potential difference, or when you see this EMF, what are these terms? What are these terms actually represent? So EMF, when you see EMF, Memuna, you will, if you just see the term, this term actually appears as if this is a force, electromotive force. But this is not a force which is present. Electromotive force is potential only, voltage only. You must have done your second chapter, electric potential and capacitance. There you must have studied about potential. So EMF is the potential only, whatever potential difference we study. So the term is a misnomer. We see electromotive force, and it seems that it's a force which is driving the cells and creating currents and something like this. No. So yeah. So one more term we have, terminal potential difference. That is also potential difference which is present in circuits. And electromotive force, that is EMF, is also a potential difference that is present in circuits. How will you identify where to use EMF, or which, in suppose a circuit is mentioned, how will you identify is this EMF or this is this terminal potential? Two things I'll tell you. Go by that. You'll be able to figure out the differences between EMF and terminal potential difference. Firstly, in an open circuit, EMF is there. Open circuit, do you understand open circuit? Open circuit means when the switch is not connected and the entire circuit is not being plugged. Means wherever there is a gap from where the current can escape and there can be a breakage. That is an open circuit. There you can find EMF, whereas terminal potential difference is present in the ends of wire where there is closed circuit. Proper closed circuit is necessary. This is one thing from which you can differentiate. Second one. Okay, so second difference is, see, external resistance and internal resistance. Do you understand? See, Memona, just tell me, this was clear? Internal resistance of a cell?
Yes, ma'am.
Okay. Internal resistance of a cell, if it's clear, it means within this battery, whatever resistance is provided, that is the internal resistance. Now, we do not just study this resistance. We have so many resistors present. We connect external resistors in our circuit. We make combinations of resistors either in series or in parallel or in combination. So, those external resistors, those actual external devices which we are connecting in our circuit to provide resistance in our circuit, those are our external resistors. Internal resistance only means the resistance offered within the cell, resistance offered to the electrolytes within the cell. So this EMF occurs in case of internal resistance. Wherever internal resistor is there within the cell, wherever in the circuit, that is the cell, of course, there is EMF. But when we talk about potential difference of the external resistor, that is our terminal potential difference. So this is how you can identify. So it is the maximum potential difference across the terminals of a cell in an open or off circuit. This I told you, when the circuit is open, so it is off. Off means, see, this is not working. This circuit, this is not working. Now see, this is the battery. This longer one represents the higher potential, and this shorter one represents the low value of potential. So high potential, low potential. So what is EMF? EMF is VH minus VH, means higher minus. If you interchange it, then what will be the EMF? Higher minus lower. It's just that you have to identify which one is higher and which one is low. For higher one, you should know that higher one is the longer bar which is present. See, when we are drawing a battery, this higher one This is the higher one, which is longer, and this is the lower one. So this is across these ends, when you take the difference, that gives you the EMF of a circuit. When we are talking about terminal potential difference, so potential difference across terminals of the cell in a closed circuit. Closed circuit means it is an on circuit. Switch is on, everything is working, wires are connected, and everything is set. Potential difference across the external resistor connected. This also I have told you means, suppose this is our circuit, a very small description of the circuit. This is the external resistor which is present. Right? External, let's say this is the final equivalent resistance. I'm not saying only a single resistor is connected. There can be many resistors connected, but this is representing the entire equivalent resistance of all the resistors which were connected. So the potential difference here is the terminal potential difference. And this, see, this is the portion of our cell. So we cannot represent internal resistance within the battery, no. So that's why we put it adjacent. So this is representing the internal resistance, which is representing, not representing where there is an EMF. Now, when the three definitions, EMF, terminal potential, and internal resistances are done, now we'll come to the calculation part and the formula part. By then, you write this part first. Okay, now see, let's relate with the formula. Firstly, the current, let's write. See, do you know, Memuna, just tell me in the first class how much we have completed? We couldn't complete certain portions that I wanted to know because we have to complete those also, not the next class. Yours was left, Zara had completed. So that's why, and Taha was also there. So I couldn't teach you specifically your part. So Memuna, can you tell me?
Yes, ma'am. We were doing uh the other chapter, not this chapter. The first class you took, you were doing other chapter.
Which chapter?
I think it was uh
No, I think we
current.
started with current electricity only, Memuna.
Yeah. This is also current electricity.
Yes, this is current electricity.
Okay. We
Uh,
were doing
I
electricity
think the
only.
did we start with drift velocity?
Yeah, we started with drift velocity.
Okay, drift velocity was done. Ohm's law. Did we do Ohm's law?
No, no.
Ohm's law. Okay, it means a small portion is left. Okay, that's good then. See, current is equal to total voltage divided by total resistance. This is what is Ohm's law. Ohm's law is basically V is equal to IR. So this we will discuss in which conditions this law is valid and when we can use this law. So current is equal to voltage. So our voltage is EMF by total resistance. Now one resistor that is present is capital R. One resistor that is present is small r. So this is the formula of current. Now, as I've told you, V is equal to IR. So if we have to calculate terminal potential difference, simply put the value of I and multiply it to R this way. So no need to remember hectic formulas and lots of formulas for this purpose. Just remember the simple basic formula. What is I? I is the current across the circuit. This is the total current across the circuit. So this is the value of current. This is the value of potential. Then there is one very important formula. V is equal to I minus E plus R is also used, and V I plus ER is sorry, E plus I have interchanged. So this is E minus IR. Now, when you are calculating potential difference across internal resistance, so it will be I into small r. When you are calculating potential difference across external resistance, then it is equal to I into capital R. Remember this. Now, if you know this, I capital R, I small r, this formula, just remember, ma'am. I'll discuss this formula in detail with you because this wasn't done with you. I'll discuss this formula in detail. So you
Okay.
know one potential is EMF, one potential is this. How can you calculate the net potential? By taking the difference. So that's why it becomes I minus E minus IR. There's a condition. We will see this formula again. We will see the details of this formula. So I'm gonna write down these formula, then try this question and answer all the four parts. This is not difficult for you to answer. Everything is done here. First you do, then I'll discuss everything with you. Start writing from here. Okay, ma'am, I'll tell you. See, this is the external resistor, capital R, because this is not with your battery. This is your battery, 22 volt. And this is your internal resistor. So what we have to do, we first have to find the current. What was the formula I told you? EMF divided by external resistor plus internal resistor. EMF is 22, external resistor is 10, internal resistor is 1. So 22 by 11 is 2 amperes. Second part, potential difference across external resistor. What did I tell you? Current multiplied to the external resistor. So current we have calculated 2 and external resistor is 10. So potential becomes 20 volt. Third part, potential difference across internal resistor. So this will be current into internal resistance. Whichever resistor it's asking you, potential difference across whichever resistor, just multiply it with the current. So 2 into 1, this is equal to 2 volt. Now you can check also. When you add these two, 20 plus 2 is equal to 22 volt, which is the total voltage present. Last part, terminal potential difference. For terminal potential difference, this is the formula E minus IR. So EMF is 22 minus IR is 2. So terminal potential difference is equal to 20 volt. These things I wanted to tell you, Mamuna, that see, when you see that current is coming from the positive terminal and it's going inside the negative, see, it's going out from the positive, going out from positive like this. Then we write it as V is equal to E minus IR. This is equal to V is equal to E minus IR. Okay. But when you see, this is what we have studied. But if you see, this is getting out from the negative one and going in the positive one. See, going out from positive, negative and going into positive. Then we put a plus sign. So if the key is open, current is 0, potential difference is also 0. This is your entire topic of this, a short topic, but an important one. Write it first. Memuna, this part I have done with you, this part. And this also, this question I have done. Did I do
Yeah.
this question, second question? No, this was left.
No, I guess I'll check it.
Okay, write it. First write yourself. Take 2 to 3 minutes. Then I'll discuss
Okay.
it. It's very simple though, but try it first. See, Memuna, how we'll solve this question. Basically, you know, the formula of current is charge divided by time. Now, we know that charge is the electronic charge. And what is the time's relationship with frequency? Time is inversely proportional to frequency. So if you put this and this here, charge is E and 1 by frequency. Frequency will go up. So current is equal to E into frequency. This will be the form. Write it. Memuna, I think drift velocity we didn't start till here only we have done. See, check this topic. We didn't do or we have
No, ma'am.
done. We have not done, no?
No.
Because in the first class, this part was left. And from the next class, you had to join from there. So that's why these portions were left. Let us complete first these portions.
Okay.
See, what is meant by drift velocity? Let me tell you. Basically, when you see a section of a wire, within that wire, positive ions are also present, electrons are also moving, the charges are also moving, and these electrons are moving in a random order. All these electrons, they are moving in a random order. So what happens here is, as soon as the switch is on, the electrons tend to drift towards the, can you tell me which terminal? Positive or negative?
Positive.
Positive. Very good. Because electrons are negative particles, so they'll tend to move towards the positive side. So very right. These electrons tend to drift towards the positive terminal of the circuit. And what happens as a result? All the electrons tend to move in a drifting manner. And that average will, see, every electron will be having its own velocity. See, the way I mentioned here. This is the V1 velocity. Here we have V2, V3, V4, V5. Like this, all these are the values of the terminal of these velocities. Now see, if so many infinite numerous electrons are present within the wire and every electron is having its own unique velocity, then we cannot say one particular velocity. We have no value for one particular velocity. Which velocity will I tell as the answer? What is my answer? I can give nothing because all these are moving with different velocities. So suppose you take this example. When you have a, suppose in your classroom, you have lots of students present and you're teaching, there are lots of students present and you have conducted a test and every student has scored a different mark. So what you will do when I'll ask you, Memuna, what is the score of your class? So will you be able to tell me the score of a single child? No, because all the marks are different. You cannot tell the marks of a single child. Every score is different. So in such cases, what do? We calculate the average. And then we say average score is this. Some students must have scored full marks. Some students must have failed also. So average marks we get, this is the average score touched by every student. So average thermal velocity is this only, U1, U2. This drift velocity is this only. This is the average velocity by which the electrons tend to drift or move towards the positive terminal of the battery. So N is the number of electrons in the conductor. Average thermal velocity is U1 plus U2. See, initial velocities. Average thermal velocity means initial velocities. So U1 plus U2 up till UNth divided by N. This is 0. Why is this 0? Because see, this has just started moving. So initially it will definitely be 0. Initially this is 0. So U1 plus U2 plus UNth, this is 0. Now U1, U2, UN, these are the thermal velocities of electrons. Just a second. Yes, Mamuna. I was saying U1, U2, U3, U4, all these are the individual initial velocities of these electrons. So we calculate their average. Their average is 0 because every electron was at rest, as we have discussed this point. So initial average velocity is C. So what is drift velocity? Velocity with which the electrons drift towards the positive end of the conductor due to application of electric field. Now F is equal to QE, and we know that Q is the electronic charge. So F is equal to Q is E is from your first chapter. And F is equal to MA you must already be knowing from your Newton's law. So from your Newton's law, A is equal to force by M. Force is equal to charge into electric field, E into E by M. So this is the acceleration. Tau 1, tau 2, these are the relaxation time. So time taken by electron into two successive collision. Means when two electrons have collided and they are taking a very small break before beginning the next collision. That is what is called as the relaxation time. And again, we calculate the average of these relaxation times. Do not write down anything, Memuna, I'll give you time. What's the final velocity? We use the equation, the uniformly accelerated equation. V is equal to U plus AT. So first one will be V1 is equal to U1 plus AT1. V2 is equal to U2 plus AT2. Vnth is equal to UN plus ATN. So drift velocity is equal to V1 plus V2 plus V3 up till nth, Vnth. So drift velocity, when you put the value V1, it is U1 plus A tau 1, V2 is U2 plus A tau 2, V3 is U3 plus A tau 3, and so on till nth. So we separate all the U terms and these A tau terms separately. See, this is what I was discussing with you, that this will be 0. U1 plus U2, this entire term, this will be 0. So what are we left with? A tau 1, A tau 2, A tau 3 and on. So what is the drift velocity? See, this is the average relaxation time. The average of all the relaxation time. So the average relaxation time, we take it as tau. So what is left? V drift velocity is equal to A into tau. And acceleration we have initially only calculated. So what is the drift velocity's formula? Electronic charge, E, capital E electric field, tau average relaxation time, M mass of electron, and Vd is the drift velocity. So drift velocity is minus E tau by M. This is the whole formula of it. And this is a relation, very important relation, which is used in the graphs also. When temperature increases, tau decreases, means the relaxation time, and drift velocity also decreases. Or you can take vice versa also. When temperature decreases, tau increases and drift velocity further increases. Tell me, Mamuna, this concept is clear, or still you have any query, any doubt in this?
No, ma'am, this is clear.
Okay. While writing, if you get any doubt, you can let me know. Okay. Start writing it from here. This derivation is important. It's very lengthy.